Okay, this is the lesson video for AP Calculus BC on section 3.4, related rates. And what I want to warn you about with this section, especially for those of you that came to AP Calculus BC directly from pre-calculus, you might find this section a little bit difficult. I'm going to show you the basics of related rates, but this is all problem solving. It's all applications of derivatives, and it's all problem solving in sort of real world scenarios. And so it's a lot more challenging than what we've been doing, because you're not just taking derivatives, you're having to apply those derivatives, and you're having to figure out the relationships to create the equations that you're going to take the derivatives of. So there's a lot more to this than just sort of blindly applying the derivative rules. So I want to show you the basics of this first, and then we'll get into really what the problem solving is going to look like. So in this first basic example, it says, suppose x and y are both differentiable functions of t and are related by the equation y equals x squared plus 3. Find dy dt when x is 1, given that dx dt is 2 when x is 1. Okay, so this is just a really basic idea, or a really basic problem, so you can get the idea of how this works without having to worry about all of the problem solving scenario. So we have y is x squared plus 3. We want to find dy dt knowing x and knowing dx dt. So you can see we're taking the derivative with respect to t. T is typically going to be time when we're talking about related rates. So when I take this derivative, dy dt is going to be equal to 2x dx dt. And then I'm just going to have plus 0. Now notice we have that dx dt attached to the derivative here. So we're taking the derivative with respect to time and not with respect to x. So I don't have a dx like we would have had before. And now at this point, this is pretty simple, right? Because I know what x is. X was 1, and dx dt was given, and that was a value of 2. So dy dt in this case is actually going to be equal to 4. So that's sort of the main idea. We're going to be taking the derivative with respect to t, which will typically be time. And then once we've got that relationship, then we're going to relate these rates together. And you can see where the name comes from. We've got the rate of change of y, we've got the rate of change of x, and we have an equation that is allowing us to compare those two rates. Okay, so let's move on and take a look at what the process is typically going to be for us. Each one of these problems is sort of unique in its own right. There's a few major sets of problems that you're going to start to see some patterns in terms of how the problems tend to set up. But the equation that you write is going to be typically unique to the problem that you're solving. So it really depends on what you're given. So when we solve these, we're going to try to follow these steps as best we can. We're going to write down everything that we're given. And when necessary, we're going to draw a sketch. Typically, we're going to need a sketch for these types of problems. The sketch is going to serve two purposes. One is that it's going to actually let you see what's going on in the problem. And the second is it's going to define your variables. So then we're going to write down what we need to find. And then hopefully we already have it. But if we need to, we'll write an equation relating the variables. And then we'll differentiate. Now remember, we're going to differentiate with respect to time. And we're not going to substitute in for anything before we differentiate unless it's a value that's not changing. If it's a constant value that doesn't change over time, you can plug it in at the beginning. But if it's a changing value, you don't want to plug it in until after you've taken the derivative. And then the last step is just solve for whatever it is the problem has asked us to solve for. All right, so I'm going to show you kind of a mid-level difficulty example, so you can get a feel for a typical related rates problem. And the hard part with this is I can only work through so many of these with you without you having to just sort of grind through the process and really kind of suffer through it a little bit and get a little frustrated trying to solve through the problems, because that's when you're really going to learn how these things work. If I just keep demonstrating how they work, it'll be helpful to a point. But then at some point, you've got to be able to just go off on your own, and regardless of what type of problem I throw at you, have the skills to sort of feel your way through it and figure out what needs to be done. So as much as we have sort of an algorithmic process we follow, we don't have, just a set way that we're going to solve every single problem, because every relationship is going to be different depending on the scenario that we're given. Okay, so I'm going to show you one that's sort of mid-level, and then I'm going to have you try a few of these, and then the rest of this practice will just be you working on Wiley Plus, and I've got some extra practice problems attached to this set of notes. So on this problem, it says water is poured into a conical paper cup at the rate of 2/3 inches cubed per second. If the cup is 6 inches tall and the top of the cup has a radius of 2 inches, how fast does the water level rise when the water is 4 inches deep? Okay, so the first thing I want to do here is I actually want to get a decent diagram to work off of. So we're working off of a conical paper cup, and we were given some information about this cup. So we had a radius up here of 2 inches. We have a height of 6 inches. And we've got our water somewhere in here, right? So for the water, depending on where I am, I'm going to have a radius and I'm going to have a height. Okay, so some other given information here. We have this 2/3 inches cubed per second. So dV dt is 2/3 cubic inches per second. Okay, in addition to that, it's not directly stated, but we know we're talking about the volume of a conical paper cup. So since it's a cone, we know the volume of a cone is 1/3 pi r squared h. And the last piece of this, which you may not recognize right away, is that I want to try to get my equation in terms of a single variable when I can. And in this scenario, I actually can. So there's some more sort of embedded given information that you don't recognize right off the bat. But look at the similar triangles that we have here. So if I were to look at that right angle there and this right angle here, you can now see how we have similar triangles. So one of the triangles would have legs of r and h. The other triangle would have legs of 2 and 6. So what I'm going to do is I'm going to write a proportional relationship here. R over h is the same as 2/6, which tells me that r is equal to 1/3 h. And the reason I did that is because, like I said, I want to try to get my function in terms of a single variable if I can. So I'm going to substitute in, I know volume is 1/3 pi. Let me just rewrite that. Got a little messy there. So 1/3 pi times my radius squared. Well, r, I'm going to substitute in 1/3 h and then times my height. So in the end, what I've got here is 1/27 pi h cubed. So I've got my volume now in terms of a single variable. Last piece that I want to do here before I start solving, let's just recognize what we're looking for and make sure that we focus on that. I want to find dH dt. And I want to find that at the point where, let's see, the height of the water is 4 inches. Okay, so that's what I'm looking for. Now, since we already got volume in terms of h, this is actually going to work out pretty well. When you first start solving these types of problems, you might not recognize right away that you need things in a single variable or that you can even get them in a single variable. But a lot of times as you solve the problem, you'll kind of realize that you don't have enough information and you've got to go back and figure out these relationships. Okay, so first thing I want to do here is I want to take my derivative of the volume function. So when I take the derivative, I'm going to get 1/9 pi h squared times dH dt. And now I've got the relationship between dV dt and dH dt. dH dt is what I want. So that's the same as dV dt over 1/9 pi h squared. Okay, so the last piece of this then is just substituting in the information that we know. So I want dH dt at the point when height is equal to 4. And when I substitute in here, my dV dt was 2/3. and my h was 4. And so there's what I end up with. And in the end, what I'm going to have for my dH dt when h is equal to 4, that's going to be equal to 3 over 8 pi. And then I just want to think about my units. My units in this case would be inches per second. Now, there's a couple things we can do to make sure that we've done this correctly. First thing, 3 over 8 pi, that's approximately 1/8. So you want to think about, does that really make sense? If I'm pouring water into this cup at a rate of 2/3 cubic inches per second, does it seem reasonable it would be going up 1/8 of an inch per second? So that's the one thing I want to think about. Does that seem reasonable? And I would say, yes, it does. Next thing is the water level should be going up. I got a positive dH dt value. That makes sense. And the last thing you can check if you really want to is you can check your units. If you go back to this previous step, remember 2/3 was in inches cubed per second. And then down here, this 4 was in inches. So we have inches cubed per second divided by inches squared, and that's where we end up with the inches per second. Okay, so the nice thing about problem solving scenarios is it's usually pretty easy to spot when you've made a mistake because, let's say somehow I flipped this answer and I got 8 pi over 3 instead of 3 over 8 pi. Well, 8 pi over 3 would have given me roughly 8 inches per second. And if I had 8 inches per second, you have to ask yourself, does that seem reasonable? Okay, so in this case, obviously not. All right, so what I want you to do is try this next problem. And we're going to do this with really the last 3 problems. I'm just going to have you try them, and then I'll go through the solution. So I want you to pause the video. I want you to draw a diagram for this. Try to write down what you're given. Write down what you're trying to find, and then try to solve it out. So take a few minutes and do that. And when you unpause the video, I'll show you the solution. All right, so here's what you should have ended up with. You can make your diagrams as nice as you want to. I tend to be sort of a minimalist with the diagrams just because I'm not very artistic. So I just put the bare basic information, whatever I have to have in there is what's there. So you can see that the height of the street light here is 20 feet. You can see that the height of this person, Pablo, is 6 feet. Some people like to actually draw a light and draw a person and all that, and you can do that if you want. But I also have 2 variables that I've defined. X as being the distance between Pablo and the light, and then Y as being the length of the shadow. Okay, so those are all defined now. My variables are defined. My scenario is sort of well defined in my mind now. I can see what's happening. And now I've got to come up with a relationship between these variables again. So similar to the last one, we actually can use some triangle similarity here again. We've got right triangles. One of them has a right angle here between those 2 legs, and then the larger triangle has a right angle here. So this relationship that I came up with, 6 over y is equal to 20 over x plus y, is just using triangle similarity. So I cross multiplied and I got a relationship between my variables here. Y is 3/7 x. So I already have y just in terms of x. Pretty easy this time. They also told us that Pablo was walking at a rate of 5 feet per second toward a street light. So you have to be really careful in a situation like this. If he's walking toward the street light, that means x is getting smaller. So I need dx dt to be a negative value. So you can see I defined dx dt to be -5. Now, the way I have this labeled out, what I'm trying to find is dy dt when x is 24. And then at that point, take the derivative of the equation. Remember, we're taking the derivative with respect to t. And then we just substitute in our dx dt, and we get -15/7 feet per second. And again, we want to think about, okay, does that seem reasonable? If he's walking toward the light at 5 feet per second, does it seem reasonable that his shadow would be getting shorter at roughly 2 feet per second? And I would say, yes, that seems reasonable. It makes sense that it's negative. It also makes sense that, the number is not gigantic. It's not really, really small. It seems like a reasonable size. So I can quickly check and at least make sure that it seems like I don't have any glaring errors in my solution. Okay, so there's another problem here I want you to try. And I put this one on here just so you could see some things when we're dealing with angles. This one's actually mostly set up for you. So I want you to give this one a shot. and see if you can come up with a solution for it. If you do it the right way, there's not really a ton of steps to it, but you still got to work through some of the basic ideas for the setup. So pause the video, work through it, and then come back here and check your answer. All right, and here's what you should have for that one. There's kind of nice ways and ugly ways to do this. A lot of this could be done on the calculator, but in terms of the hard part of this problem's really already been done because they told you the relationship, right? They already told you that S is equal to 50t squared. They've got a nice diagram here with a theta in it, with an S in it. They told you tangent theta is S over 2000. So they gave you almost everything that you need. So it really just then turns into how do you want to go about solving this? So I know I have all of these things that are given in the diagram. So I want to find d theta dt because I'm looking for the rate of change in the angle of elevation. I want to find that when time is equal to 10 seconds. All right, so we use that relationship that tangent theta is S over 2000, and then I just substituted in the idea that was given here is that position is equal to 50t squared. So now I have theta directly related to t. So what's a little bit different about this one is I have a t in my equation. So when I take the derivative with respect to time, the chain rule piece of it on the t part of the equation, it's just going to be dt dt, which is 1. Okay, so at this point, this simplified down into tangent theta is t squared over 40. Took the derivative on both sides. You can see that I got a d theta dt here, but I didn't write the d theta, or excuse me, the dt dt over there because it wasn't necessary. And now I'm just solving for d theta dt. And then the last part of this, depending on how you want to go about it, you may or may not need a calculator for this. And what I chose to do was actually get the solution without having to necessarily rely on the calculator for everything. So what you could do in here is you could find theta, and then you could go through and figure out what t over 20 secant squared theta would be equal to. What I did was I figured out, okay, what is secant theta? So the way I did that, you can see on my diagram, is I said, all right, if this is 2,000 feet from the camera out to the launch pad, and if I know we're at time is equal to 10 seconds, then we can figure out the height of 5,000 feet, and then that allows me to find the hypotenuse. So I didn't simplify it all out. I just kind of wanted to show you where this came from. So now secant is the same as 1 over cosine. So if I know the cosine of the angle, I can just take the reciprocal of that. And that's what I did right here. I just took the reciprocal of the cosine, and then from there, you just plug it into the calculator. So pretty simple to do. From a calculus standpoint, a lot of the stuff that seems difficult in here is all of the trig and all of the algebra that you have to do. What you'll find on these problems is that there's not a lot of calculus in them. There's a lot of prerequisite material in them that's going to be the majority of the work. So if you really look at this closely, the only step where we did any calculus on this problem was right here where we took the derivative. Everything else in this problem was dealing with trig, dealing with algebra. So it's other things, outside of just this whole idea of taking the derivative. So keep that in mind on these problems. That's what's challenging about them, is that you've got to rely on a lot of your prerequisite knowledge to be able to solve these problems out. All right, so last problem that I have for you here is actually an old AP multiple choice question that I wanted you to take a look at. So the reason I wanted you to see this is that when these are AP multiple choice questions, they tend to be fairly short and simple. Sometimes you'll see these questions and they'll be AP free response questions, which is designed to be essentially a 15-minute question. So depending on what format you get these questions in, they can be really easy or they can be really hard. And so this is a multiple choice, so it's a lot easier. I want you to just pause the video and I want you to try this one and see if you can come up with a solution for it. Okay, and here's what you should have ended up with for that one. You should have gotten D. So the relationship here is a little bit different. You can see that we've got a ladder falling down, it's slipping down the wall. And we've already got a diagram, so I know what X is, I know what Y is, and I know the ladder is 15 feet. Now, notice in my equation when I solved this out, I substituted the 15 in immediately. The length of the ladder is not changing. So for my relationship, x squared plus y squared is 15 squared, I didn't put in like a z or anything like that because I knew that the rate of change of that ladder is going to be 0. Okay, so then we just took the derivative, and then from there, what I'm looking for here is dx dt. I know, let's see, they told us that x was 9, so from that I can get that y is 12, and then they told us what dy dt was, and we just have to solve for dx dt. So I didn't show all the steps in this case. Typically with the multiple choice, you don't really need to show a lot of work, but I wanted to give you kind of the main idea of what my thought process was in solving that problem. Okay, so as you work through related rates, definitely you want to work all the problems in Wiley Plus, obviously, because you've got to turn that in. But in addition to that, and especially for people that have not seen this before, the more practice you can do with related rates, the better off you're going to be. So what I did here was I attached a worksheet to this. You don't have to turn this in. I just wanted you to have a lot of problems to work off of that were similar in difficulty level to the types of problems I'm going to expect you to know how to do. So I gave you 12 questions here, and I also gave you solutions to those 12 questions. So use these for extra practice. Definitely start with what's in Wiley Plus, and then you can supplement with this worksheet if you feel like you need more practice. So like I said, these are, for some of you, these are going to seem really difficult at first, but you will find that the more of them you do, the easier they're going to get. All right, so we'll talk about some of these next time in class, and you will run into some that are going to be more challenging than the ones that I went through just now. I'm just trying to give you the basic idea so that now you know what to do when you approach the problems, and you sort of, you've got to keep an open mind when you're trying to solve these because you never know what type of relationship you're going to need to solve the problem out.